Winslow Hansen, for the folks who might not know who I am, especially online. I'm an assistant scientist here at the Carey Institute, and I have the distinct pleasure of hosting our seminar speaker this week. I'm thrilled to introduce Claire Schollaert. Claire is a postdoctoral associate at the University of California, Los Angeles in public health, but she lives in Seattle, where she did her PhD at the University of Washington. And she has a really diverse research portfolio, especially for somebody in such an early career stage that transcends climate science, public health, smoke chemistry, atmospheric chemistry, and even some disease ecology, which I was surprised by. I've known Claire for, well, like quite a few years now, actually. She's a part of our Western Fire and Forest Resilience Collaborative and is doing really exciting work of modeling how much smoke is produced, where it goes, and who's affected by it from the simulations that I work on with other collaborators. And so I was just really excited when I convinced her to be able to come and give a seminar here. So without further ado, let's welcome Claire.
Hope this microphone is working. Sounds like it is. Cool. All right, thanks so much, Winslow, and thanks for the invitation to have me here. I just want to start off by saying that while I work with Winslow and some of the other Carey folks on wildfire and smoke-related work, that is not at all what I'm going to be talking about today. And I'm going to be talking about some work that's sort of a fairly new area for me in terms of infectious disease land, but maybe more relevant for some of the disease ecology folks in the room. Let me just put this there, cool. But as Winslow said, I'm more of a public health person, so I'm an environmental health scientist. So I work under this umbrella of public health that's really interested in environmental exposures and how those impact people. And what I wanted to talk about today was this data problem that some of us in the climate and health space have been thinking about, but it was maybe a data problem that's relevant for some other folks who are also thinking about climate impacts more broadly. And that data problem or question being, how do you pick an appropriate climate input data set for whatever downstream climate impact you may be interested in thinking about? And I'm going to be talking about this in the context of valley fever in California as a case study. And this is just some foreshadowing here. This is not a smoke plume picture up here. This is actually a dust plume going through the Central Valley in California. And it turns out is an important transmission mechanism for valley fever itself. So taking a step back just for a minute to think about climate and health more broadly, this is a really chaotic figure for the American Public Health Association, but I think the chaos kind of sends an important message in and of itself. But there's this, all these different pathways through which the changing climate is impacting environmental exposures and how that's impacting downstream health effects, anywhere from rising temperatures contributing to more extreme and frequent heat waves, a worsening heat island effect, which we know is associated with a range of adverse health outcomes, including heat stroke, respiratory outcomes, cardiovascular outcomes, et cetera. We can look at extreme weather events and thinking about the worsening flooding, coastal storms leading to things like property loss, infrastructure damage, water contamination, which we know is associated with waterborne illnesses. Mold exposure post-flooding is also a really big concern, which we know has downstream respiratory impacts. And so this list goes on into the air quality related impacts, the vector-borne diseases. There's all these interconnected pathways and the ways in which climate change is getting worse. It's leading to these increases in these various environmental exposures and these downstream health impacts. And a couple other things I wanted to highlight here is that not everyone is experiencing these exposures and health impacts in the same way, in that low-income communities, communities of color, unhoused populations, people with pre-existing conditions are all disproportionately exposed and impacted by these climate-related hazards. I also just want to highlight that it is the job of our public health infrastructure, whether that be the federal level, the state level, our county level health districts, to manage these risks. So they're the ones in charge of designing interventions to mitigate these exposures and downstream health outcomes. They're the ones in charge of preparedness efforts. So we know that climate change is worsening. We know that we may see these increasing risks down the line, and public health agencies, rightfully so, are really starting to think about like, okay, what are these exposures going to look like in the future, and what can we do to prepare? And so how do we do that? So this is sort of a very oversimplified framework of how we can think about projecting disease burden as a function of climate change into the future. It's probably fairly similar to some of the other frameworks that folks use in other climate impacts work to project climate-related outcomes moving forward. But generally, in order to project future disease risk, we need multiple of these components. So we need climate projections. We need, what is temperature and precipitation, for example, projected to look like in the future as a result of a changing climate. We need an understanding of baseline disease prevalence or disease incidence. So for example, how much asthma do we know already exists in a certain population or geography that we're interested in? We need an exposure response function, which is really central to what environmental health is looking at, or environmental epidemiology in particular, which is just an equation that links a certain amount of exposure to an environmental contaminant to a specific amount of a health outcome. So how many additional hospitalizations as a result of asthma maybe we expect to see as a result of, say, like a 10-unit increase in air pollution exposure. And then we need population characteristics, right? Which is just census data for the most part. So in the environmental health space, we are fairly comfortable with these last three components. It's this first piece, where this climate projections piece, where we tend to be pulling from the climate science world, which is totally fine. There's a whole field of brilliant climate scientists who are doing really awesome work to model our global climate system and our regional climate systems. They're churning out all this awesome modeling data. They're putting it, on these online platforms, making it publicly available for us to use, so much so that, those of us interested in climate impacts work, when we're reaching for these data sets, we're often met with this choice of what input data set we can use for any given analysis. So data sets can vary in their spatial resolution, their temporal resolution, and the methods used to generate them. And the project I'm going to talk about is really motivated by this choice. So there's all of us in the climate and health space who are really pulling for these data sets without perhaps a great understanding of the implications of using one product over the other. And it turns out valley fever is a great case study for this, for reasons I'll get into in a minute. Just taking one more step back, so our understanding of, this is probably familiar to a lot of you, but our understanding of the global climate system comes largely from these large global climate models, which do all this work to simulate, sorry, this is kind of blurry, simulate these interactions between the atmosphere, the land surface, the oceans, vegetation dynamics, and can incorporate the role of different forcings on this climate system. So the role of anthropogenic emissions, for example. And what we get from these global climate models is this understanding of what climate has looked like historically from a simulated perspective and what it may look like in the future in the form of these gridded climate variable estimates. So estimates of temperature, precipitation, humidity, et cetera, at this global scale at fairly coarse grid cell resolutions. So at least 100 kilometers in spatial resolution, for example. For those of us who are interested in regional to local climate impacts, though, that spatial resolution is really not going to cut it. But thankfully, there's a whole group of brilliant climate scientists within the broader field who are interested in this concept of downscaling, or how do you take this coarser scale global climate model, or GCM outputs, and force them into resolutions that are more usable for the rest of us. This is an example of kind of what that looks like at a high level. So on the left, you have, this is just an example of precipitation outputs from some random global climate model covering California and Nevada at about 160 kilometer grid cell scale. And you can see there's kind of only a handful of grid cells that are covering both of these states. And then on the right side, you see an example of a statistically downscaled version of this data set, downscaled to about 6 kilometers. And what you can see now is a lot more of that precipitation variability in places like the Sierra Mountain Range, the coastal mountain regions of California, a level of granularity that's a lot more useful for us when we're thinking about regional to local climate impacts. So it turns out there are a couple primary ways that folks can go about downscaling these climate outputs, each with their own pros and cons. One of the primary ways is through dynamical downscaling, which uses high-resolution climate models nested within global models to simulate these regional climate processes. Dynamical downscaling is super great because it can really capture and represent these physical processes that are driving the climate system. So land-ocean interactions, land-atmosphere interactions, the role of vegetation dynamics, topography, et cetera. And as a result, you can get fairly highly and temporally resolved climate model outputs from this. The downside of dynamical downscaling is that it's really expensive. It's expensive from a people perspective, from a time perspective, an expertise perspective, a computational perspective. The other major bucket of downscaling is the statistical downscaling approach. And there are several different types of statistical downscaling, but they all sort of use these statistical relationships between large-scale climate patterns and local observations to generate regional climate data. The great thing about statistical downscaling is that's really fast and easy and cheap. And the result of that is that you tend to have a lot more options in terms of scenarios that have been downscaled. So a lot more GCMs have been downscaled, a lot more emission scenarios, for example. The downside of statistical downscaling is that it's really dependent on these historical relationships and assumes that those relationships are going to be static moving forward into the future, an assumption that is probably not going to hold true in certain systems. And there's also a more limited ability to capture these smaller scale physical processes, so precipitation across complex terrain, for example. So I mentioned that there are several different statistical approaches out there. One of them is this localized constructed analogs approach, or LOCA, which is the one I'm going to be referring to moving forward here. And the reason for that being that there's been this big push in California as part of the state's 5th climate change assessment to do a ton of downscaling to generate a bunch of fine scale climate output for the state to use in the assessment itself by the state agencies, as well as researchers and practitioners. The state has made this big push to put all these downscaled climate data sets up on this really nice and easy to use online platform where anyone can go and grab these data sets. And they're really encouraging end users, whether that be on the practice side of things, the management side of things, or the research side of things, to come and grab these data sets and use them in their own work. That said, there's fairly limited guidance on this beautiful data visualization or data management platform on what to choose when and why. I think the sort of limit of the guidance, and I'm oversimplifying here, but the limit of the guidance they provide is if you are interested in more extremes, take the dynamically downscaled outputs, and if you're interested in more GCMs or emission scenarios, so you're more interested in the spread of possible climate futures, pull the LOCA, the statistical downscaling data. So this is why I bring this back to valley fever and climate and health researchers more broadly who are increasingly reaching for these types of data sets in our climate and health work without a super great understanding of the nuance between them. And as I said, valley fever turns out to be a great case study to probe this question a little bit because the outcome is really dependent on these wet, dry precipitation patterns throughout the year. So we're said, okay, great, let's go and throw both of these downscaled products at this problem and see what we get on the tail end. At this point, some of you, maybe less so in the disease ecology world, but some of you may be wondering what valley fever is, which is totally fair. It's not an outcome that you all have to think about a ton on the East Coast. It is very much a West Coast growing public health crisis. These are just some headlines from the past year or so highlighting sort of the alarm coming around valley fever in places like California in particular. It's a fairly challenging outcome to diagnose and track. And again, it's a growing public health crisis that the West is thinking really critically about. Again, some foreshadowing. I have this screenshot from the New Yorker, I think, on this article where they titled it Death Dust, with dust exposure being one of the transmission mechanisms that's fairly important. And so valley fever, or coccidioidomycosis, is caused by inhaling spores of the fungus coccidioides. This fungus lives in soil. The spores can become airborne when the soil is disturbed by things like construction, dust storms, wind, agriculture. There's a tentative link to wildfire events, though the mechanism behind that is still unknown. Two possible pathways for that are that the wildfire itself is contributing to soil disturbance, which is facilitating spore release. And then the other potential mechanism, or perhaps they are both true, is that the spores can actually travel through wildfire smoke plumes themselves. But we have seen these spikes in incidence following some of these wildfire smoke events, so there's some folks thinking about that. But as a result, of this airborne spore risk in exposure via inhalation is our primary concern here. And so when spores are inhaled, respiratory impacts are our most common symptoms that we see, though they're certainly not the only impacts, where we're also seeing symptoms like fatigue, fever, night sweats, muscle or joint pain, chest pain, weight loss, rash. The sort of spread of possible symptoms makes it a more challenging outcome to diagnose. Also, as a result of this specific airborne exposure pathway, certain groups tend to be disproportionately exposed. So agricultural workers, for example, which makes sense as a population who works a lot around soil disturbance, construction workers, folks that work on natural gas extraction sites where there's a lot of digging. There's also been reports recently on increased rates of valley fever among incarcerated populations in California. So there's some potential environmental justice concerns that we need to be worried about here. In terms of the distribution, as I mentioned, this is largely a Western US problem. This is a map of the distribution of the fungus itself in orange across sort of the southwestern region here, with this pocket up in southeastern Washington and northeastern Oregon, which is a fairly new development in recent years. And then the hatch marks show the potential distribution as a result of environmental conditions. This is not only a North America problem, the global distribution extends down into Central America and these pockets of South America as well, in eastern Brazil, and this pocket in sort of northern Argentina, Paraguay, Bolivia as well. So zooming in on California a bit more here, the endemic region in California specifically is really prominent in the southern half of the state. This map on the right is showing average incidence per 100,000 residents at the county level. So the more yellow colors show higher incidence rates, and we can see sort of the valley, the Central Valley popping up as a hotspot. So the Central Valley is sort of the agricultural hub of California. It's where the rest of the country gets a lot of its fruit, vegetables, nuts from. It's a major producer. Then we also see these hotspots coming up in the central and southern coast. Valley fever is also not evenly distributed throughout the year. It turns out to be a very seasonal outcome. So this plot on the right is showing monthly proportion of total incidence in these highly endemic counties, where the darker colors show higher incidence or proportion of incidence. And you can see there's a good deal of variability based on where you are in any of these highly endemic counties. But generally, we see the season start to pick up in the early fall and wind down late fall, early winter. And the reason for that is largely climate driven. So there's this hypothesis called the grow and blow hypothesis, which follows that these wet winters allow for a lot of fungal growth, followed by this spike in temperature in the summer, and the hot weather allows for those soils to dry out, those spores to become airborne, leading to inhalation exposure. So these plots are from a figure from Jennifer Head's paper, who's a collaborator on this work, where she was looking at climate drivers of valley fever in California specifically, where we have, again, incidence on these maps on the top, incidence on the left, mean January rainfall in the middle, and then mean July temperature on the right, just to sort of see the spatial distribution of some of these climate variables. And then looking at the bottom here as we start to understand a little bit more about that grow and blow hypothesis or pattern here, where we have this plot of monthly incidence or proportion of cases in purple here, where we see this spike in cases start to pick up in the fall and then wind down as we sort of approach the winter, which tracks with how we understand the climate to work in this part of California. When we have this wet season that drops off in the summer, obviously the warmer months are the late summer, which it seems to track with when we're seeing these cases. Cases tend to drop off when we get these sort of season-ending precipitation events, similar to how the wildfire season ends in the West, for example. This is just another look at the seasonal effect from the same paper. These plots on the left are showing incidence rate ratios as a function of precipitation on the top and temperature on the bottom. These incidence rate ratios are just metrics that we use in the environmental health world to measure the amount of disease cases over time in this case. And these are monthly rate ratios 3 years following this major transmission year that we see on the right. And we can just focus in on the first or the last 12 months following, or 12 months preceding this major disease onset event in the fall, where we see this spike in precipitation in the winter months relative to previous years, followed by this hotter summer than they've seen in previous years, which was followed by this big valley fever season that they saw in California specifically. So we know that valley fever is seasonal. It turns out modeling seasonality generally is quite difficult. Some of you in the disease ecology space may know about this better than I. This is certainly not my area of expertise. But luckily, a brilliant environmental epidemiology PhD student, Simon Campaneri at Berkeley, who's a collaborator of ours, has taken on the task of developing this model for valley fever seasonality in California specifically, where he's using Markov processes to estimate or simulate the probability of transition between the aseasonal and the seasonal state, where aseasonal is the non-valley fever season, seasonal is the transmission season. And he built this original model using incidence data at the census tract level that he got from the California Department of Health from 2000 to 2020 using climate data from PRISM. And what he got from this model, this is relatively hot off the press, but he can come up with these probabilities of season onset and season end at the census tract level, which is shown as an example at a high level on the right here, I think at like a sub-county level of the highly endemic counties. So we know that valley fever is seasonal. We know that it's very linked to climate. We know that the climate is changing, and California is certainly not isolated from those effects. With this worsening valley fever problem that we've been seeing, it makes sense that our natural next question of what might this look like moving forward in the future as climate change gets worse. Which brings us back to this framework that I mentioned at the beginning here of how we can project future disease burden. So now we have a few of these components that we need here, right? So we have this fun seasonality model from Campaneri et al. That allows us to sort of have this exposure response function. It's not a traditional exposure response function because we're not necessarily linking exposure to an actual health outcome. We're looking at seasonality as an outcome, but that's trivial. We can still use it in this form. Then we need our climate projections piece. I mentioned that we are data rich in California when it comes to climate projections. So when we were thinking about this project, we had this question of like, okay, well, is it better to use the LOCA data or the dynamically downscaled data? And the question was, we did not know at the beginning of this process. We weren't sure how each of these downscaled products characterize the wet, dry seasonal patterns in this part of California. And given that that was so important to this specific outcome, we thought, okay, let's try them both because we have the data available to us. So we pulled data from 3 GCMs for one SSP or one emissions scenario for both of these downscaled climate products that are available for California. We grabbed the PRISM data as sort of our historical reference. We take some census data, we throw this all together, and what we can get at the tail end are these projections of valley fever transmission onset week, end week, and season duration for these 3 different time periods. So historical from 81 to 2010, mid-century, and end of century. So I want to first just start by looking at what some of these climate variables look like across these methods before we get into any of the projections piece. So on the left here, we have plots of monthly average temperature on the top and cumulative weekly precipitation on the bottom. Weekly is certainly a strange temporal resolution to be using here for a lot of us, but that is the temporal resolution at which the seasonality model was built because that's the format in which they could get data from the California Department of Health, and that's sort of just the nature of working with health data. So we're working at the weekly scale here, aggregated to monthly. So when we look at the historical data in terms of temperature, we can see things track decently well. Both of the downscaled methods slightly overpredict temperature relative to PRISM that we're using as our reference here. And then the middle and right columns are showing change by mid and end of century, estimated using both of these downscaled methods. Some variability, but like temperature change is tracking decently well across these 2 methods, which is encouraging. Looking at precipitation at the bottom, things are tracking decently well. LOCA tends to underpredict some of that winter precipitation. There's also a lot more variability in precipitation, as you might expect generally. And then as we look to what we're seeing in the future in terms of change relative to the historic period using both of these methods, we see across the board sort of this increase in winter precipitation, which we know is what's projected for this area in California. We're seeing more of that increase in the dynamical downscaling scheme relative to the LOCA statistical data. That becomes a bit more exaggerated by end of century, where we're still seeing this increase in precipitation. Under the dynamical downscaling scheme, we also start to see this dip in fall precipitation, which I'll get into, but that effect is a little less pronounced in the LOCA data. So what does this look like spatially? Again, at the top here, we have temperature, the bottom's precipitation. These right 4 panels here are what we see historically and for both temperature and precipitation across the both of these downscaling methods. Things track decently well. And as we looked at change or relative change in future temperature in terms of temperature by mid and end of century, by mid-century, things look comparable in terms of increases. By end of century, we maybe see slightly more warming in the southern region of this endemic area under LOCA that we don't see in dynamical downscaling. And then when we look at precipitation on the bottom, by mid-season, things look comparable. Maybe there's some slight differences, and then we see this divergence. I'm hoping the colors are showing up. You never really know with screens. But by end of century, we see sort of across the board, dynamical downscaling is projecting this continual increase in precipitation across this endemic region, whereas under the LOCA 2 downscaled data, the southern half of this endemic region is actually seeing a slight decrease in overall annual precipitation. So things are starting to diverge a little bit. So we can dive into that precipitation component slightly more here. This is another plot showing monthly cumulative precipitation under each of the 3 time periods under both of the downscaling methods, where dynamical is in that dashed line and the solid line is LOCA. And what we see is, like, yes, we're seeing this increase under both downscaling methods in terms of winter precipitation. LOCA is generally showing less rain in the model relative to dynamical downscaled data. But what we see as both of these, as we move throughout the century using both of these downscaling methods, is this potential consolidation effect of precipitation into this core wet season, which is hard to see on this big screen, but this middle light blue panel is considered this core precipitation season, and a dropping off of precipitation in the gray shoulder seasons here. So there's potential difference across both of these downscaling methods, which is a bit trickier to see here, but is hopefully a little easier to see here. So a lot of previous work has shown that the precipitation precipitation season in California is projected to get sharper with climate change. So the wet season's going to get wetter, and the dry season's going to get drier. And it turns out the degree to which we see that does vary a little bit depending on which downscaling method we use. So on the right here, I have this historical sharpening ratio, which is this ratio of core wet season cumulative precipitation to shoulder season cumulative precipitation, with these darker colors and these higher ratio values meaning a sharper precipitation season. So most of that rain is in the core season relative to the shoulder seasons. Again, historically, between the simulations from both of these downscaling products, things look similar. Slightly different story when we start to move further into the century, where the top row, looking at LOCA, is sort of this mixed effect by mid-century, where we're seeing the sharpening in the coastal areas and maybe a slight decrease in sharpening in the Central Valley. And then as we move to the end of season, we see this really stark consolidation relative to LOCA's historical simulations of the precipitation season into that core wet season. And we do see sort of a similar effect when we use the dynamical downscaling data, but it's a lot more muted, it's a lot less pronounced than what we're seeing from the LOCA data on the top row. So what does this mean for valley fever seasonality projections? Starting out with just a very high level view here, these are median estimates of season onset on the left and season end week on the right. Week of year is on the bottom. Again, I know that week of year is kind of a weird temporal indicator, but I can walk us through what this means from like a monthly perspective. But starting in the top row, we have LOCA in purple and the dynamically downscaled outputs in blue. Things shape up decently well with both methods, maybe slightly showing a slightly shorter season relative to the reference. As we get to mid-century, we see the season onset weeks start to creep up earlier, and the season end weeks start to get more delayed under both downscaling methods, perhaps slightly more so with the LOCA 2 data, and then that continues as we get to end of century, where these season onset weeks are starting to creep into early summer-ish, and then season delay is entering into January under both methods, but maybe slightly more so from the LOCA 2 generated data, but it's a little hard to see at this aggregated level. So let's look at what things look like spatially. So just starting with the historical period, these are on the top row maps of the spatial distribution of the valley fever transmission season onset week, end week, and then duration calculated using this PRISM reference. And so what we see from this is that valley fever season starting earlier in the Central Valley, that agricultural region, and starting a little bit later in these coastal areas. The colors make end week a little bit hard to see because there's actually not a huge difference here, but season end week tends to be a little bit earlier in the Central Valley relative to the coast. But overall, seasons are a lot longer in terms of valley fever transmission in the Central Valley inland areas relative to these coastal endemic regions. But if we look at the bottom two rows, we can see how things are shaping up when we calculate those same estimates using dynamically downscaled data in the middle and LOCA2 hybrid downscaled data on the bottom relative to those historical estimates. And what we see for season onset week is that both methods predict slightly later onset weeks, about 0.3 to 0.4 weeks later, and those match between the two of them decently well. They're also predicting slightly earlier season end weeks in the middle. And then when we look at season duration on the right, we see that the dynamically downscaled data are estimating about 0.7 weeks shorter historical valley fever season, while the LOCA2 hybrid data are estimating about half a week shorter. But among both of these methods, historically, particularly shorter seasons relative to what we see in the reference for in the central inland valley region. So the historical data in terms of the GCM simulations or the downscaled GCM simulations are doing decently well. They're not perfect, but they're doing okay. But now what do we see moving forward? So these are maps of the relative change in season onset week, valley fever season end week, and season duration, all relative to each of these downscaled historical simulations. So you're always comparing the dynamically downscaled historical simulations to the dynamically downscaled future simulations. And so the top row is showing mid-century, the bottom row is showing end of century. And there's not a ton of difference by mid-century. Perhaps we're seeing slightly greater delays in end week in inland areas using the LOCA data that we see a little bit less of using the dynamical downscale data. By mid-century, season durations are perhaps a bit longer under the LOCA downscale data in the Central Valley relative to the coast, where maybe the slight opposite is true under the dynamical downscale data, where we're seeing greater season duration extensions in the coastal regions. But when we look to the end of century, some of those differences become a little bit more pronounced, where looking at season onset week by end of century, we see this sort of earlier onset or shift towards earlier onset on those coastal regions relative to the inland Central Valley under the dynamical downscaling data, whereas we see a little bit more of a uniform distribution of change for the LOCA data, or even perhaps a little bit less of that move earlier in the coastal regions. When we look at season end week, again, just a little bit more of a pronounced delay in season end week across the board under LOCA relative to what we see in the dynamical downscaling data. And then looking at season duration, we're seeing overall a greater extension in season duration across the board when estimated using the LOCA2 downscale data, particularly in inland regions relative to the coastal areas. Whereas if you look at what we estimated using the dynamical downscaling data, we actually see this greater extension in season duration in the coastal areas relative to what we're seeing in that inland Central Valley, that agricultural region. So there are some spatial differences here. So some high-level takeaways from this specific work was that we saw that under both of these downscaling methods, the valley fever seasons projected to start earlier and later and be longer over the course of the century. That said, the extent of these changes does vary depending on downscaling method, particularly by end of century and particularly across space. And so I think, just in the case of valley fever, specifically in this endemic area of California, we think it's important to consider how selection of downscaled climate data will impact projections of valley fever specifically, but also potentially several other climate-related health impacts. Like I want to zoom back out to this chaotic pathways figure of all the different ways that we know that climate change is projected to impact health moving forward. And it's possible that we need to be thinking a little bit more critically about what we're using for downscaling product across several of these outcomes, but maybe not for all of them, right? So looking at rising temperatures, again, for the very specific region in California we were looking at, the temperature data actually matched up decently well, right? Like there was some variability, there wasn't a ton of difference in terms of projections moving forward, so maybe it doesn't matter as much which product you're using for temperature. Maybe that's not the case. We're looking at extreme weather events, so things like coastal flooding, extreme precipitation events. Maybe there would be some difference that needs to be thought about a little bit more critically when picking a downscaled climate product. This certainly could be the case for other sorts of vector-borne infectious diseases that maybe depend a little bit more on intra-annual precipitation cycling. And I guess like this is a time where I like to make a plug for interdisciplinary collaborations. I think a lot of us in the climate impact space, certainly in the climate and health space, are not climate science experts. And it can kind of be outside of scope for a lot of projects to expect a lot of us to take a really deep dive into the climate mechanisms and climate science that's driving the nuance between these products. If people have the time and bandwidth to do that as they're starting a project, that's awesome, but that's not always the case in terms of what we scope out for a lot of this work. So if folks don't have the time to take a really deep dive into the climate science literature for their specific region of interest, that's where it can be really great to call your local climate scientist or the person who spent all that time generating these downscaled outputs that we're using in these analyses. I am biased in my perspective on this because I've only had extremely positive interactions with folks who have been working really hard to generate these downscaled climate data, where they are more than happy to talk through what we're seeing in their data, what we're seeing in our downstream impacts data, and how to interpret some of these results in the context of differences in nuance that they understand to be true between these different products that we wouldn't necessarily understand. And some of it is really just expert opinion at the end of the day, right? Like some of their considerations aren't always published in the climate literature about the differences between these products, but it takes conversations with some of these folks to just pick their brain about what they know the mechanistic drivers of this to be true. Like we can't validate future climate projections necessarily in the same way that we can validate historical observations. So sometimes it just takes someone who thinks about this day in and day out of like what's happening in the dynamical downscaling models that's leading to these differences of precipitation patterns, and is that more or less reasonable for what we might expect for this region? So that is my plug to get to know your local climate scientist a little bit better. But I'll zoom out one more time to say that this is certainly not just a climate and health data question that we've been asking. I imagine that there are several other climate impacts where we can be thinking a little bit more critically about the implications of what products we're using and any of these specific outcomes we might be interested in. There's certainly many wildfire outcomes far beyond the public health impacts of wildfire, which maybe we may be sensitive to choice of downscaling method, post-fire regeneration, certainly maybe drought conditions, and food insecurity and the economic impacts of climate change as a result of that, coastal hazards, logistics planning, emergency response planning, flooding, perhaps coastal ecosystem resilience. And this isn't to say that, all of these outcomes are going to be sensitive to choice of climate product, but it's perhaps worth slightly more thought than at least some of us in the climate and health space have been giving it. And I'll also just note that, as I said several times, California is data rich. Not everywhere is data rich. There are parts of the United States, there's certainly areas globally where you do not have choice of product. You maybe have one downscaled product available to you. You maybe have no downscaled data available to you. And I would still say that even in those contexts, it's important to understand what those data limitations mean in terms of the downstream outcomes you may be thinking about. Even if you only have one downscaled product available to you and it's a statistically downscaled product, that's great. But it, I think, would go far for us to understand a little bit more what some of the nuance associated with these products means when we're trying to think critically, plan for the future in terms of climate preparedness, climate resilience, and mitigation, and what these input data sets mean for us. So I will wrap up, I guess, with one more plug to the interdisciplinary collaboration piece of this. This work is largely a bridge between all these wonderful environmental epidemiologists in the middle here, several who are at Berkeley, Michigan, and UC San Diego, who think about valley fever a lot more than I do, but came to us originally with these questions about climate data. I fall into this side over here, the exposure scientist interdisciplinary connectors side, where Miriam, Marley, and I like to think a lot about how to better link earth science data, climate data to some of these public health questions. And then on the end here, the last member of our linkage is our climate scientist collaborator, who again is just more than happy to talk about all of the potential end uses for his data. I was emailing with him yesterday asking how to interpret certain slides that we hadn't talked about in a while, and I couldn't say enough good things about having your local climate scientist on speed dial. They are stoked to have people using the data that they're churning out. So I would just highly recommend continuing these sorts of conversations. And I'm happy to take questions. We have plenty of time.
Questions. And I'll be, sorry, just really quick, I'll be doing the interpretation for the online audience so she can think about answers.
Yeah.
Does the fungus on the valley fungus, does it like particular types of soils, or is it just like the climatic conditions that enable it to spread?
So the question is, does the fungus that underpins valley fever like particular soils, or is it all about the climate drivers that creates conditions where people catch it?
That is a great question that I don't know the complete answer to, but the answer is yes, there are certain soil conditions. What those exact soil conditions are, I am not sure. So I can get you in touch with the brilliant environmental epi folks that do think a lot. There's also a lot of good soil folks on this team, on this extended team too. But there are several other non-climate related drivers that are contributing to transmission. One interesting connection is a potential rodent connection. So they see higher concentrations of cocci in rodent burrows, particularly post-drought. So a lot of these rodents can be carriers, but they don't get the disease themselves. And then in drought conditions where the rodents die in their burrows, and the fungus can survive through those drought conditions, they're seeing these spikes in concentrations in rodent burrows, for example. So there's several other non-climate drivers, even though there's a drought connection, but there's several other non-climate drivers.
Yeah, Tara.
So I know in recent human infectious disease climate work, there's been a push to incorporate thermal performance curves of vectors or the infectious diseases themselves. And I'm just wondering, is much known about the thermal optima or the thermal maxima of coccidioides? And is that incorporated into models or projections?
That is a great question. That's not incorporated into the seasonality model, but this team's also doing work on just projecting incidence distribution moving forward as well. So not like when the season's going to happen throughout the year, but how many more cases and the geographic distribution of those cases. And it turns out, we've seen from previous work, there is this upper temperature threshold that the fungus can survive. And it's interesting that you bring this up because I was just reviewing Simon Campaneri's paper on his most recent incidence projections where he was only using the LOCA data for now. And we were talking about, does he need to redo or do a sensitivity analysis with the dynamically downscaled data? Because, again, preliminary results, but they're potentially seeing this decrease in incidence in the southern half of the endemic region because temperatures are getting too high and they're reaching that threshold that the fungus actually cannot survive. But we do see slight differences in how the LOCA data, the dynamically downscaled data, are projecting that temperature increase in the southern half of that region, where LOCA is getting hotter than the dynamically downscaled data. We're not sure if that's enough of a difference to reach that temperature threshold or not to negate that drop-off that they're seeing in cases, but it's potentially something that we'd look into.
So can we take an online question really quick? So we have an online question. Are there plans to use other case studies, for example, in the Eastern United States related to, for example, tick-borne illness?
That is a great question, and I think the collective, we are super open to that, and I would love to chat with someone who is interested in thinking about these sorts of sensitivity analyses there. We're obviously very California focused here, and we thought about this in sort of the wildfire context and some other sort of compound climate exposures on the West specifically, but I think there absolutely could be implications for tick distributions in the Northeast. So yes, but not any near-term projects for us specifically.
Great.
I'm just going to follow up a little bit on Tara's question about the thermal optimum, which I think is interesting because if you have a high thermal optimum for growth of the fungus, you might also imagine that things like wildfires could kill spores, but things like wildfires also kill the rodents. And there's a hypothesis for cocci where the dead rodents serve as places where the fungus can grow. So I wonder if you guys are kind of thinking about small mammal death post-fire as reservoirs for growth of the fungus that would have otherwise been killed off.
That's
So
really interesting.
let me repeat the question for the
question.
Sorry. So the question is high thermal temperatures like after wildfires can kill the fungus, but it also kills the rodents, and those dead rodents can serve as reservoirs potentially. So are you thinking about those dynamics in your work?
That's a really great question. Not me specifically, but some folks in this group are looking at the impacts of dead rodents on cocci concentrations, but not the post-fire angle. And the fire connection, I think, has been fairly hard to pin down as of now, and something that we've been chatting about. And there's a group that I'm forgetting up in Idaho who's been looking at spore transport in plumes and potential pathogen agents post-fire. So I think there are connections to be made there, but this group hasn't specifically been looking at the post-fire rodent death, but that's a really interesting point to be made that I will bring to them.
Super awesome talk. Thank you so much. Just to play off of that, I wonder, it seems like there are two components of the soil. There's like where the fungus can hang out and where it potentially is a reservoir for rodents, and rodents are acting to spread it, but then there's also the act that it needs to get turned to dust, right? Are these both, like when you talk about the demographic, the range shifting for the viruses, is that just the initial conditions for where it shows up, or also how it can be kicked up into dust and done with transmission?
Yeah, how it gets kicked up is really important, both from like the rate at which the soils dry out. So if we're having a particularly hot summer and those soils dry out faster than we usually can see these spikes of incidence because the spores can become airborne earlier in the season. But again, we're seeing connections between a lot of sort of more like infrastructural soil disturbance. So like things like industry. Yep. So a lot of spikes around construction sites. Natural gas drilling in this area is a pretty big thing. So that's a major concern. The fire disturbance, again, is really understudied, but hopefully something we can look at in the future.
Ian?
Have you all thought about how public health guidance should change potentially based on what your modeling outcomes are showing? And I ask that in the sense of like, if the season's going to get longer, you pretend you have the exact, like the perfect conditions to have a really big spike in valley fever. And people who are in like LA, San Diego, Orange, Riverside, San Bernardino counties, if we have Santa Ana wind events or Diablo wind events, do you think like this would inform and public health guidance would be like, hey, you really should limit your any time outside, even if there's no like we can't test the air for it, but these are exactly the conditions.
So how should public health guidance change based on your results?
Great question. And some of this gets into sort of the flexibility of the public health system generally and how reactive they can be to things like this. I mean, there's already some work between some of the groups that are doing some people in this group actually who are doing near-term seasonal forecasting of like what's the season projected to be, and then they feed that information directly to CDPH or the California Department of Public Health, where they can do what they do best, is like push out regionally targeted guidance in advance of what they might anticipate to be a bad valley fever season. There's also been a push working with the occupational health agencies to start to coordinate better guidance around outdoor workers. For example, there's like a very strong alignment between this transmission season and the growing and harvesting season. So ag worker exposure is a really big deal. So I think that's exactly where sort of the research to practice link wants to go. Public health dollars are really limited, and as government institutions, they can take time. They're not the most agile institutions, but that's where the departments looking at this want to go. I don't think we're quite there yet in terms of being that reactionary.
So let's take an online question. We've got Rick Osfeld online. He asks, evidently there is vast underreporting of valley fever in California and nationally, and also many exposures don't result in illness.
Mm-hmm.
So how confident are you in the epidemiological data on reported incidence rates of valley fever?
Yeah, I mean, we certainly think that there's underreporting of case data. Like I said, it's hard to diagnose. It's also hard to link exposure to the time when people are actually start developing symptoms. The other complication here is that we think that a lot of exposure can happen in workplace settings or when you're not at home. And so when the surveillance data will link your case, for example, to your home address and not to your work address. So sort of exposure misclassification in terms of our understanding of the distribution of incidents, that is certainly a limitation. So yes, we are, with a lot of public health outcomes, we're worried about exposure misclassification and underreporting, particularly with exposures that can be workplace related.
So I want to jump in and ask a question myself, if that's okay. And shockingly, this is going to be about the climate data.
Mm-hmm.
One thing I didn't mention when I introduced you is that Claire also does a tremendous amount of consulting with government agencies like EPA. She's worked with the Western Governors Association before, so she does a lot of communication of her science. And one of the things that I'm really curious about is, like, you highlighted that just the downscaling method can lead to uncertainty in our future climate projections. But then layered on top of that is GCMs vary from one to another. And then we have emission scenarios that adds another layer of uncertainty. Mm-hmm. And so when you have this tremendous amount of uncertainty, how do you communicate that to non-scientist audiences in ways that still get like a key message across in terms of, and here's an action that you might take?
Yeah, that is a core goal of public health practice, and it's so hard and we're still bad at it, right? And so when you add in all these uncertainties as we start to get into the climate and health space of all this spread across GCMs, don't even take downscaling into account right now, spread across GCMs, spread across emission scenarios, and then trying to communicate that to public health folks who don't normally think about that type of variability for those specific data sets on a regular basis, and then having them communicate that to the public, I think is really challenging and something we struggle with. I think it's the role of, internal public health practitioner workplaces to do the job of, developing their guidance based on the spread of uncertainty that we're seeing, and in my opinion, to take a more precautionary approach to prepare for the extremes. And then good public health communication is much more simple than we would want it to be as researchers when we want to caveat everything about uncertainties. And we're like, we wouldn't say that. We actually would say this with like a million caveats. And that is not what people want to hear when they're making decisions about whether they're taking their kid to the playground on Saturday. They want one number and they want to be convinced that they can trust it. So it's incredibly challenging to distill this amount of spread to a public health practice agency who needs to interpret that spread and then needs to, get it down to a one-liner that goes out in a social media post about what you should do about your kid's soccer tournament on Saturday. So it's a pipeline that is really challenging. Historically, the pipelines haven't been the most interdisciplinary, so I think there's a growing need to sort of get more Stefan Rahanys in those conversations and people who are great climate science communicators. Public health practitioners are trying to be really great communicators, and it's something they're great at, but they could use some help when it comes to incorporating some of these external disciplines. And there are some superstars who are great at that, and the more that we can get those folks involved, I think, the better.
Right. Any last questions? Yeah, Adrian.
Given the importance of precipitation, do you know if like irrigation or any other clean water inputs play any sort of role in that?
So the question is, how might irrigation or human alteration of water cycle might play a role?
Knowing limited amounts about that, my assumption would be yes, probably particularly in the agricultural exposure settings. They're not incorporated, as far as I know, into a lot of these climate-driven epi models, as far as I've seen. But I mean, considering water management in California more broadly, that's a really interesting component. I think that should be incorporated that hasn't really, to what I've seen. Maybe I just don't know, but that's a really good point.
All right, let's give Claire another round of applause. So Claire will be in the lunchroom for the next hour if you have other questions or want to chit chat, and then she'll be around for the rest of the day.